Hey, good morning. Almost done. Today, last topology for high power factorized converters. And up to this point, as derived topology from not converter, we saw the full bridge. We saw the half bridge. We saw the forward. And there is one extra that we will analyze. Just as a comparison of properties of these different topologies, stresses basically, the primary side. Secondary side is something that you already know. Let's suppose that switches have a current I and a voltage V if you design it as a full bridge. I mean, I could be 3 amps, V could be 300 volts, whatever it is. This is the maximum stress of your transistors. For a given power, given voltage level, etc. If you design, instead of full bridge, a half bridge, stresses are something like this. The voltage stress in a full bridge or half bridge with the same input voltage, the same output power, same everything else, the voltage stress going from full bridge to half bridge stays the same. So we have the same voltage stress because there are two transistors stacked one on top of the other, and the maximum voltage of each transistor sees is basically the supply voltage, the input voltage, the DC bus voltage. On the other hand, if we look at the current in a half bridge, currents are twice as much than a full bridge. So here my current stress will be 2I. So we see that both these topologies are okay for high voltage input, but the full bridge can handle higher power because its current stresses are lower. One half of the current stress in a half bridge, or half bridge has twice as much. Why? Because here you have two legs for transistors. Here you have only one leg, two transistors in series. So basically the voltage stays the same, but the current becomes twice as much. What about forward? In a forward transistor, in a forward converter, the voltage stress is quite high because we have the reflected voltage from tertiary to primary point. So the voltage threshold will be 2V twice at least, actually it's more than 2V because there is the ringing, there are spikes, etc. And current, if you compare with this design, with the full bridge design, is also twice as much, 2I. Why? Because you have only one transistor, one leg, one possibility for current to go down. So they don't share current. So you see that this is a low power topology because it stresses both in voltage and current, the only unique single transistor you have, a switch you have. This goes better because it has still a high current stress, but lower voltage stress. And this is even better because you have low voltage stress and low current stress. But you pay for this reduction in stress because here you have 4 switches, here you have 2 switches, and here you have 1 switch. There is one extra item, one extra topology over here. Can you imagine what could this extra topology have over here? If it is a topology that is used, it means that it has something different from those. Because if you have a topology that has exactly the same properties, let's say that has a full bridge, half bridge, one of the two is more convenient and the other one will die, not be used. Here there is another topology different from this, with different properties. And can you imagine what is this topology? No, the characteristic. I don't want the high voltage stress and low current stress. That means this will be a topology adapted for medium power, low input voltage, because the voltage stress on the transistor will be twice as much as the input voltage. So if you start with from a low input voltage, that's okay, but the current will be low, so you will have a higher power handling capability as a whole. And this topology is a push pull. Okay, there is still one extra topology over here, that is the two transistor forward, but we won't analyze it because it's not very useful. Two transistor forward looks like this one, has the same properties as a half bridge, but it does not use correctly, briefly, does not exploit 100% of the time of the transformer, so I don't like it. Push-pull. Push-pull has an input schematic that is something like this. You have a transformer with two primary windings connected in series. Each of these primary windings has NP and NP turns. Oh, please. I still saw a couple of days ago misunderstanding between winding and turn. Winding is the set of turns that are on a magnetic core. Turn is the single path around, one single turn around the core. So a winding is made of a wire that makes many turns around the core. In Italian is avvolgimento and spira. Avvolgimento is winding, it's all the electrical part around the core. Spira is just a single turn, the single path around the core. Don't tell me faccio 4 avvolgimenti. No, you don't make 4 windings, you make 4 turns around the core. And we need to drive the core once with one polarity and the next cycle with a different opposite polarity. And this is obtained, oops, I killed somebody. Takes here the central path to positive Vn, and the two ends of these two windings are connected to the ground with two transistors. S1 and S2, like this. What about the secondary side? It depends on what voltage you need on the output. If you have a low output voltage request, you can use a center path rectifier as usual, but this is the standard stuff. If you need to supply a high voltage at your output, a high output voltage, you can use a what? If you need to supply a high output voltage, what kind of rectifier do you choose? Grades. For diodes, like this. Output is still the same, rectifier is still the same. No matter what is the input, if it is half bridge, full bridge, push-pull, whatever, the output is either one of these two. Actually, you can have 2 more different rectifiers, but we won't analyze that. This is the input structure, and as usual, we drive the two S1 and S2 switches in a non-overlapping way. S1 and S2. And S2, and we try, for example, these two switches like this. This is the driver signal for the transistor, S1, and this is the driver signal for S2. Those are interleaved, that's standard story, as you know. And what happens to the primary winding if we apply this kind of driving signals? Well, when we close the switch S1, we apply positive on non-dot, and so we will have a polarity in the transformer. We will have all the positive on non-dot. And when we close this switch, there will be this diode D2 working. Then we open S1, not driving on the primary winding. The primary winding is open. There will be the key off. That will be the key off time. Current will recirculate through the two diodes. Then we close S2. And when we close S2, we apply the positive on the dot. So the magnetic flux inside the transformer that was climbing in the previous cycle will start to decrease. And the standard story. When we close S2, there will be the first diode conducting, the second diode is off. Okay? If we go back one moment, to the our circuit this time is T on, this time is T off, and as usual, when we have a double polarity driving or double polarity rectification, we have this period of time and the related frequency is this switch. That means this switch and the F switch is the period for the waveform applied by the switch or to the switch, and this is the period of the switch period of the signal applied to the switch. And we have also, if we look at the secondary side, if we look after the rectification, we have also this period of time that will be T bar and corresponding the F bar. Because when we rectify the double two-way rectification, we just take all the pulses and put them together. Current over here will be something like this. Current over there will be something like this. This is the standard stuff. What about the input capacitor? What does the input capacitor see as current? Well, this input capacitor sees, experiences both the current that goes to S1 and the current that goes to S2. That means that this input capacitor sees, experiences frequency, a switching frequency that is twice as much as the switching frequency of the S1 and S2 switches. This capacitor works at the same frequency as the buck converter is working. And the current that flows through this capacitor is the current given by all these pulses. So the duty cycle that this capacitor sees is the buck duty cycle. It's not the switch duty cycle. It's not the transformer duty cycle. Okay? Those are basically the very same considerations I made for both full bridge and half bridge. So far so good? Still with me? Okay, what should we know to design this kind of topology? We already know that this is a topology used for low input voltage, and we will see why. This is a medium power topology. You can make hundreds of watts, kilowatts, if you need to go with this topology. first thing we need is to find out the ratio output voltage divided by the input voltage, as usual. We already did this calculation, both for a full bridge and half bridge. For full bridge, I started from the input and I moved to the output. For the half bridge, I started from the output and I moved back and brought back my equations to the input. Both are fine. Whatever you choose, it's okay. Let's go from input to the output here. So, looking for V0 equals, let's start from the input. From the input, we have a V voltage applied to the primary of my transformer. Oh, I forgot to mark that this is NS and NS. Is all the input voltage applied to the winding? No, there are voltage drops along the path, along this loop. And so, we will start with V in minus, what voltage drops do you see in the input path? Switch minus this switch. How many switches do you have in series to the input? One only. This is a signature of a low voltage system, because you have a low voltage at the input and you are not wasting your low voltage input with two voltage switches, two switches drops, only one. Minus possibly RS. It's not the RS yet on this circuit. I don't know if I will put RS or not, because I don't know if I can control this converter in current mode or voltage mode or both, whatever. But just to play safe, let's put here RS. What I forgot to put in this parenthesis, I forgot because I don't know how to evaluate it.
The resistance of the wire.
The wire resistance and the primary. That makes a voltage drop that reduces basically the effective voltage that is applied to the ideal primary winding. This voltage is transferred to the output side via the turn ratio, and the turn ratio is NS over NP. This output voltage on the secondary side is applied to a buck converter, a low-pass filter basically. And the low-pass filter extracts the average value of this voltage, and the average value is just the peak voltage, that is this one, multiplied by this side, D. And we still have to consider the voltage drop across diodes. They're both during T on and T off. There is always one diode in series to the output, or two diodes in series to the output. It depends if we use a central tap or a full bridge. And so here I should still subtract minus number of diodes times PD, the voltage drop across your diode. If your diode is a Schottky diode, voltage drop is half a volt, a little bit more. If your diode is a standard NP diode, your voltage drop will be around 1 volt or so, even a little bit less, more. If your diode is a silicon carbide Schottky diode, and 2 volts, 1.8, 2 volts, something like that. Okay, that's it. And so, we still need to specify if this value is minimum or maximum. We have to specify if D is minimum or maximum. Actually, maximum or minimum, because it goes the other way around. And as usual, we put here minimum input voltage, and we put here maximum duty cycle. Why do we put here the maximum duty cycle? Because the maximum duty cycle is something that I want to control. I want to be able to decide. Maximum duty cycle must be as large as possible, because the larger the better. The larger the better. I exploit full time my magnetic core, my magnetic component. If D is large, I exploit better the current, the switches, so the current stresses to the switches will be lower. But if my Dmax is too large, well, if my Dmax, for example, is set to be 1.2, well, no, there is something that does not work. You cannot use 1.2 duty cycle. 1.2 in a duty cycle is meaningless. If your duty cycle is 0.95, yeah, probably you could have it working, but you have no dynamic head through. That means if you need to increase suddenly the output current, and to increase the output current through the inductor, you need volts and seconds, you need voltage and time. You don't have enough voltage to be applied. So this Dmax, something reasonable but not too high, 0.8, 0.75, 0.85 if you don't have a very fast changing loads. And if Dmax, this is the bucket duty cycle obviously, if this Dmax is around 0.8 and you go current mode, you need for sure compensation line. That's definitely right. What can you derive from this equation? Well, if we design Dmax, the only quantity you can derive, and you have to derive from this equation, is NSLNP as usual. So NSLNP, and this ratio will give you all the stresses, voltages and current stresses. NSLNP equals V0 plus number of diodes times VB, it depends on your output voltage, divided by this expression that is Vin minus V switch, one V switch because we have only one switch in series to the primary, minus VRS times the max. If we put here the minimum input voltage, and as usual when we get to this number we add, just for safety, just to be able to come up with a few percent, don't say 5, a few percent of this term ratio. Plus a few percent is a good number, 5% or so. This term ratio has not to be an integer number. This term ratio will be approximated by a rational number because the number of terms are integer numbers. But even if it is 2.7, that's okay. Because 2.7 could be 27 on one side and 10 on the other, or some other rational solution. Okay? So far so good. Then, what should we find now? That's exactly the same path that we followed for full bridge, half bridge, forward, and overward. Stresses and power dissipation. Stresses, the buck section on the output side is still the standard story. It's designed exactly as buck converter. So critical inductance based on the minimum load, etc., etc. Stresses. On the primary side, obviously, because on the secondary side we already saw it. S, in and in the capacitor. S1, S2, dot up. This is the primary section. Let's check what are the voltage and current stresses on each of the switches. Let's see how to design this sensing resistor and how much power it dissipates. Let's see what is the current stress to this input capacitor. Well, that's easy. Let's start with current. IS1. Current flowing through S1. Oh, by the way, these topologies are a very nice feature. And this nice feature is that both S1 and S2, all of its switches are low side refer to ground, so they don't need strange circuits to like transformers or bootstrap circuits to drive a high side switch. IS1 has a shape that is exactly the current on the secondary side during T on moved to the primary side. So it will be something like this. Here's the secondary current during T on moved to the primary side. And we know that this average flat top approximation, the average of the pulse height, this will be something like I naught times
NP over NS.
N over N, sure, P over S or S over P?
P over N.
S over P over P over S, S over P, S over P. Because we are going backward from the secondary to the primary, but we are transforming current, so it's the other way around. And this current change, current variation, that is not important for the stresses, for RMS value, it's a very good approximation. This ramp, this current change, this current ripple, is basically the current ripple on the secondary side, on the inductor, moved to the primary side. So if you know that your output current goes from 10 amps to 12 amps, and your turn ratio is 10 to 1 to 10, you will have that the primary side, your 10 amps will become 100 amps, your 12 amps will become 120 amps. Ouch. Yeah, very high current. Bad example. Next time I will give you a better example. And on top of this current on the primary side, there is also a magnetizing current. And the magnetizing current is something like this. And here there will be the other current. But the magnetizing current will have as an effect to increase a little bit the slope of this torque. Okay, it's not so important. It's not so important for the stresses. This current pulse has a duration that is this width. And now you can find whatever you want from this waveform, because I switch average is equal to what is the average of this white waveform?
I naught times NS.
I naught times NS over NP times the switch. I switch RMS is equal to
I naught
approximately equal to, what is a very good approximation, I naught times NS over NP times square root of the switch. Do we need this value?
for
This
the
quantity?
windings.
Sure. This is to find out the losses, conduction losses into the transistor, into the MOS transistor. We need this value to size the wire gauge to decide how heavy must be our wire, because the RMS current is related to all everything that is resistive. Do we need this value? Basically not. It's not important for the winding, it's not important for the transistor, unless you use BJTs. If you use BJTs, the average current is important, but if you use MOS, it's not important. What if you use IGBTs? You don't use IGBTs in this topology, because this is a low voltage topology. IGBTs are a high voltage device. You cannot find IGBTs with a voltage rating less than 600 volts. Those are high voltage devices. This average current is important because it allows you to double check if your calculations are right or not. Because this average current plus But this average current comes from the input, from here. So this average current multiplied by the input voltage gives you an estimate of your input power. If you are designing something that has to deliver 200 watts and you have an input power of 100 watts, there is something bad, wrong. If your input power is 3 kilowatts, it's even worse. If your input power is around 200 watts, that's okay. That's fine. What about this peak value? Peak value is equal to the output peak current to the inductor, and you know how to find the ripple on the other side, moved to the primary side via some ratio. And if you want to be very precise, but you can't be very precise, if you want to be very precise, you can also add 1/2 of the magnetizing current. But you cannot be very precise because in the first steps of design, you don't know yet what kind of transformer you will have. You don't know yet what will be your magnetizing current, magnetizing inductance. You can have a guess, but it's just an educated guess. Most of the time, this magnetizing current is absolutely negligible for stresses. Could be, but important for the RS definition, because RS sees all the current, including the magnetizing current. But this magnetizing current usually is small compared to the primary current, usually. Then you have to double check at the end. Okay, so far so good. What about voltages? On the switch. This switch. Obviously, this switch during on phase and during off phase, there are two voltages across the switch. During on phase is a quantity that we decide with some common sense. Common sense means in Italian. Buon senso. No senso comune. And this is few percent of the input. Because every percent of voltage drop across the switch on is the corresponding percent loss in your efficiency. You want to have a low voltage drop of your switches because your input voltage is already low. But don't exaggerate, don't say, oh, my input voltage is 10 volts and I want 1 millivoltage voltage drop. Because it means to use a huge, and when I say huge, I mean huge MOS transistor, and this MOS transistor has to be grilled. And when you drive a large MOS transistor with a lot of silicon, you have a large input capacitance, it becomes slower and slower. So there are advantages and disadvantages. Few percent of me use your common sense. If your input voltage is 10 volts, well, you can have a voltage drop of 0.1, 0.2 volts across these switches. In some cases, it's just a matter of efficiency. In some other cases, if you have a too large voltage drop across the switch, your power dissipation in the switch could be critical. It could be difficult to remove heat from there. But off, this is something that we have to be careful about. With in, when you close this switch and the other switch obviously is open, let me put the dots down just because I like positive numbers better. When you close this switch, you apply a positive voltage on this half winding or this primary section with the positive on dot. it means that all other windings will have positive on dot as well. And here we will have a voltage across this unused primary winding with a positive on dot. How large is this voltage on the unused primary winding? V, because the two ratios, the two windings have the same terms. So I will have here V in, and this V in is connected in series to V in, because it starts from V in. So the voltage over here will be twice V in. And this is the two that they put on your table previously. My voltage stress on this transistor is high because of this transformer effect. But it's not finished, the story. Because when you close the switch over here, you get something like that. Let's see, this is S1, this is S2. Let's go to see the S2, the voltage across the switch 2. When I close, at this point in time, I close S1. Well, the voltage here was V in, because both the switches were open, and the center of the transformer was connected to V in. When I close S1, what do I get on S2? The voltage jumps up to V in. You wish because an open switch is a capacitance. Here you have a parasitic capacitance. Here you have a parasitic inductance, and guess what? You have an LC circuit, and you apply a voltage step to this LC circuit. So what do you get? Resonance. And this will start to resonate like this. So, as usual, you have some extra voltage. During this period of time, the S1 is closed. Here, this is T on for S1, this is T off, and during T off, the voltage comes down back 0. 0 means the A. Do we expect to have a very clean step over here? No, because as usual, you have a step applied to the LC circuit, so you will have some ringing over here. But this ringing is not dangerous from the stress point of view, because the voltage over there is already low. And then, here we go T on for the second transistor, T on this one, and when you close the switch, what happens to the voltage across the switch? Goes to 0, well, almost 0. And it goes to a very low voltage. This is T on of T2, and then bad news at this point. What happens when you open the switch? Well, when you open the switch, if you are very naive, you could expect, oh, it goes back to the A. Because if you open the switch and it is still open, nothing is driving the input voltage, the output, the secondary windings are short circuited by diode. So my voltage should go back to the A. But you already know that there is an LC, and this LC will give you ringing. Yes. Are you worried about this over voltage? No. It's not a big thing because you start from A, not twice A. But here there is a very bad phenomenon that occurs. And this phenomenon is called bad luck of engineers. Because at this point, look at the circuit how it is. You have this switch closed, you have a lot of current flowing through these parasitic inductance, through these leakage inductance, Why a lot of current? A lot of current because this is a medium power, low voltage topology. So you can have a lot of power going to the secondary side with a low input voltage. Low input voltage, a lot of power means large current. And this large current flows to these leakage inductors. When you open with a switch, this to an inductance, you open the switch, what happens? You have the inductance gets mad, si incassa come una biscia, and it generates a very high voltage spike. Not 20-30% or usual rating, no, that goes very high, because here there is a very large current in this inductance. And you can have a very narrow pulse, 50 nanoseconds, something like this, but it goes up, 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 up. And guess what happens right here? Boom. Boom. Boom, boom, kaboom, depends on what language you speak. This happens every time you are opening an inductance with the switching series and you don't provide for a circulation path for this. This partially happened for in a flyback converter, but in a flyback converter it's not so bad because it's not a high power converter, it's not a high current converter. But this overvoltage can be blocked somewhere over here using, for example,
clamp diodes,
Zener diodes. There's not so much energy for it here, but it's enough to kill your transistor. You can use clamps, Zener diodes for high-speed Zeners in this application. You don't use standard Zeners. You use a specific components. They are basically Zeners, but designed for this application. They are able to absorb a very large energy for a very short time. And those are called transistors or TVS, transient voltage suppressors or things like this. Or you can use specific snuffers, not RC snuffers as we are used to design. To stand these oscillations, you can use an RC snuffer as we learned in the past. But for this peak, you cannot use a snuffer that has a different topology, a different circuit. I don't have time to explain this. Or you can use a transistor over here, Zener diode, but you have to plan this. Otherwise you risk kaboom. A few months ago, there was a design of this kind of converter. It was a 2.5 kilowatt converter starting from 50 volts in. So if you have a 50 volt input voltage, the maximum stress that you expect from these switches is 100 volts. And so we picked 150 volts apart, 150 volt transistor. And then I told this company and the student that was working on this stuff, on these schematics there are no transistors, there are no snuffers yet. You have to put the snuffers on these circuits if you want to work it working correctly. But in order to design the snuffers, could be just a Zener, could be a more complicated snuffer, you need to know the parasitic elements of this transformer. And you don't know these parasitic elements unless you have the transformer in your hand, unless you have mounted the circuit. So my idea was, I hope you understand that you have to start with low voltage, low power, measure the ringing, measure the spikes, evaluate them, and then put the snuffers and go up in power. Well, my message was not understood like this. They tried it, oh, it works, they went full voltage, full power. And guess what? There were two large MOS transistors each side, because each of these switches were made by two transistors in parallel, and they exploded basically. And I told them, be careful. Then we measured this voltage spike, starting with the low voltage obviously, and we found out that this voltage spike was around 6 times the input voltage. So if the input voltage is 50 volts, they got 300 volts on this transistor. That was a 150 volt path. This transistor worked for many minutes, and then eventually it gave up and said, okay, if you want to play very hard with me, I don't play with you anymore. When you pass the actual maximum rating of a component, it does not mean that it fails immediately at that point. It can survive. But if it fails, you can complain. Not only, but if you go above the maximum, absolute maximum rating of a component, even if it survives, well, it could get crippled. So its reliability goes down, the electrical performances can go down, so on and so forth. Okay? That's good. So the voltage stress over here is a little bit more than twice as much as this input voltage, provided that you have some kind of a spike in voltage limitation. In some cases, it's not a big deal. If your converter is not too high power, not too high voltage, you can also forget that. But for high power converters, that is an issue. An example of application for this push-pull converter is your car. If you have one of those monster amplifiers in your car, those audio amplifiers delivering 2 kilowatts, 1 kilowatt, and that need extra battery, and when you pump up the volume, the car is just starting to inflate and deflate every time you have a boom on your speakers. These amplifiers, these audio amplifiers in a car, these audio amplifiers, in order to deliver power, even reasonable power, like 50 watts, 100 watts or so, they need voltage. They need 30 volts, 50 volt supply voltage. In your car, you have 50 volts available. The standard is 12 volts, 14 volts if your engine is running, 10 volts if your battery is low and your engine is not running. So, the only way to boost up the car voltage is not to use a boost, because a boost is a single transistor, is not a so powerful converter. A good way to boost up the car voltage is to use a push-pull, because this is the ideal input topology for the low input power, and in the turn ratio you can get an output voltage that is 50 volts, or plus minus 50 volts, positive and negative 50 volts, to supply your amplifier, with a power that is few hundred watts. This is the ideal converter for audio amplifiers in a car. Because the input voltage is low, the power required is 100 watts or so. This is what you usually do. Okay? Do we control it in voltage mode or current mode? Because before going to find the stresses and find if the stresses of the sensing resistor, I need to know if I need a sensing resistor. Okay, you know that you can control these converters both in voltage mode, in general, in voltage mode or current mode. For this kind of converters that are full, with a full rectifier, full wave rectifier on the output, that means you use completely the transformer, both with positive and negative pulses, you need to be sure, you have to make sure that you don't apply a DC component on the primary side, because if you apply a DC component on the primary side, what happens is your fluxes start to run away and eventually the transformer saturates. And I told you that you have two ways, actually there's a third one but I don't want to teach it because it's bad. You have two ways to control the flux runaway. That is the imbalance on the voltage applied to the primary winding. What are these two ways? Capacitor in series that absorbs this small DC imbalance, or current mode, because the current mode monitors the total input current. So if you have a magnetizing current running away, it will add to one pulse and subtract to the other pulse. And so one pulse will be narrowed and the other pulse will be enlarged. And so the current, the magnetizing current is kept centered around the 0 volt area. One of these two methods has to be used. Which one? Let's see, can we put a capacitor in series to the primary winding? If we put a capacitor like T, that is series to the two primary windings, we make a bad mistake. I think in French it's called the cancre. Did you ever read the book La Foire au Cancre? No, that's another book. C'est un bouquin, c'est un vieux bouquin. Si vous le trouvez, La Foire au Cancre, c'est le recueil de toutes les bêtises que les étudiants ont dit dans les écoles.